Hi there, this is Matt Heffernan. Welcome back to my channel. This is the 12th episode in a series that seeks to demystify programming and assembly language for the 6502 family of 8-bit processors. We're using the Commander X16 as a target, as it has a 65C02 and is a particularly excellent platform for this learning process. If you haven't seen the previous episodes and need to start at the very beginning, please go back to my channel and don't forget to subscribe and click the bell for notifications while you're there so that you'll know when the next episodes come out, and start this playlist from the beginning. So far in this series, we have learned the fundamentals of assembly programming by going through the entire 65C02 instruction set and examining how each instruction works, and then how to do basic things with the kernel and the VERA display controller, including interrupts. In this episode, we are going to go further into how VERA works by learning about graphical tiles. In earlier episodes, we only dealt with text layers, and text glyphs are tiles, but treated in a very different way from tiles that can have more than just a background color and a foreground color. Of course, building images from tiles is nothing new. Humanity has been doing it for millennia, from classical mosaics to Renaissance stained glass windows to modern computer graphics. For systems with limited bus bandwidth, tile maps are a very efficient way of moving pixels around, and were the basis of many computer displays throughout the 8-bit and 16-bit eras. While the X16 also supports bitmap modes, it's the tile modes that are best at creating dynamic and responsive user experiences. As we saw in our earlier video introducing the VERA video adapter, there are two layers that can be configured, populated, and displayed. We had an example program that made use of two text layers, but one or both of those layers could have also been configured as graphical tile layers. These require the developer to define their own tile imagery and lay them out in a tile map, much like we had done with the text layers. These tile maps can be of various sizes, from 32 by 32 tiles to 256 by 256 tiles, and can be configured to use tiles of a specific color depth and fixed dimensions. Text tiles that can use the built-in glyphs from ROM are encoded as 1 bit per pixel, or 1 BPP, and are 8 by 8 pixels in size. This means that each glyph is defined by 8 bytes, with a byte for each row starting at the top. Each set bit indicates which pixels are foreground, and the clear bits indicate the background pixels. Text layers can only make use of 256 different glyphs and come in two modes: 16-color text with separately configurable background and foreground colors for each glyph on the map, and 256-color text with a system default background color fixed and use of any color in the 256-color palette for the foreground of each glyph. Graphics tiles make use of greater color depth, using more bits to define each pixel. The tiles can also be different sizes, with each dimension being 8 or 16 pixels, but a single layer can only have one consistent tile size and color depth. You can also have up to 1,024 different tiles for each graphical layer, which means that VRAM is going to be more of a limiting factor, as greater sizes and color depths require more memory to store each tile. However, the maps are still the same, using 2 bytes to define each tile instance, which will encode the tile index and other data used by VERA to render each tile. The color depths for graphical tiles can be either 2 BPP for 4 colors, 4 BPP for 16 colors, or 8 BPP to have each tile use any color from the full 256 color palette. These same color depths, including 1 BPP, can also be used for bitmap layers, but we'll get into those in another episode. We also won't be getting into sprites either, but they are very similar to tiles and can be either 4 BPP or 8 BPP, but have the freedom to be placed anywhere on the screen on an individual basis. We'll see how that works in yet another video, but for today we will show how tiles can be in a fixed location within a map. However, we will also see that maps are not static and can be quickly updated and even scrolled around. We also saw in our first VERA video how the layer configuration registers work, at least as far as text modes go. Let's take a closer look to see how they can be modified to work with graphical layers. The config registers at hex 9F2D and 9F34 define the overall mode of their respective layers, as well as the map dimensions if used as a text or tile layer. We saw before how the default text layer was 128 by 64, so it had a default config value of hex 60, because a map height of 64 has a value of 1, and the width of 128 has a value of 2. This makes the upper nibble 0110 in binary, or 6 in hex. The rest is 0 because we have a 1 BPP color depth, and we are not in 256 color text mode or bitmap mode. As you can see, we can adjust all of these things for any layer, using 0s for having a map height or width of 32, or 3s for 256. To make the layer a graphical tile set, we keep the bitmap bit clear and put a non-zero value into the color depth. A 1 will get us 2 BPP, 2 is 4 BPP, and 3 is 8 BPP. So we could have a huge 128 by 128 map of 256 color tiles by setting config to hex F3. Of course, that doesn't mean you should. VRAM budgeting starts right here, so you need to understand the diversity and contiguous size of the map you need, and how much of the palette you need for each tile. A lot of the time, you don't really need the whole palette for a single tile, and 16 colors will be sufficient and cut your tile size in half. Remember, you only have a little over 126 kilobytes of VRAM to work with, and that has to fit all the maps, tiles, sprites, and whatever else you need to have visible all at once. The map-based register is 0 for the default text layer, because its map starts at the very beginning of VRAM. In our earlier video, we set up another layer's map to start right after it, at hex 04000, which we specified by writing hex 20 to map base, which is 04000 shifted 9 bits to the right. We have to do this because we can only specify the upper 8 bits of the 17-bit address that mapbase is referencing. This means that all maps need to start at addresses aligned to 512 bytes, making the lower 9 bits of the address all clear. The tile-based register also requires an aligned address, but this time it is further constrained by only the upper 6 bits, meaning that the lower 11 bits need to all be clear, requiring a 2 kilobyte alignment. Those extra 2 bits are needed to specify the tile dimensions. As the default text layer has 8x8 glyphs starting at hex 0F800, this means tile base needs to be set to hex 7C, which is the starting address shifted 9 bits to the right and the lower 2 bits left clear. Setting either of the lower 2 bits will specify a height or width of 16 pixels. This is the other big driver of VRAM usage, as you need to determine what is the most efficient use of your tile data. Bigger tiles mean you can use smaller maps to cover the same area, but your map diversity might make smaller tiles more efficient, allowing for more reusable tiles. So, how to decide? Let's take a look at what each tile mode really means. The most basic graphical tiles are 2 BPP, which gives you only 4 colors on each tile. Using 2 bits for each pixel means that each byte defines 4 pixels, requiring at least 16 bytes to define an 8x8 tile, or as many as 64 bytes for a 16x16 tile. You don't have access to the whole palette in 2 BPP mode, only the first 4 colors of each palette offset, and really only 3 colors, as index 0 will always be transparent. Using a palette offset of 0 means that indexes 0 to 3 in your tiles will map to exactly the same indexes in the full palette. By default, this gives you black, white, red, and cyan. But really, black is just the default background color. The pixels in the tile set to index 0 are transparent, not an opaque black. The same goes for other palette offsets, such as 1 that will remap the indexes 16 through 19. But the color at 16 also won't be used, as those 0 pixels will still be transparent. There's also no way for 2 BPP tiles to have access to colors past the first 4 of any palette offset. This makes them pretty limiting, but that was good enough for systems like the IBM PC with CGA graphics, or the original Nintendo Entertainment System, or Famicom, where everything was a 2 BPP tile or sprite. Here we can see what an example of an 8x8 2 BPP tile could be, using the default palette. Each row of pixels requires 2 bytes, and any pair of bits that are both clear will specify a transparent pixel. We can see how this binary bitmap translates to 16 hex bytes below, and that is what would need to be written to VRAM for this tile. Next we have 4 BPP tiles, which will give you all 16 colors for a specified palette offset. This means you have access to the full palette across your map, except for colors that have indexes that are multiples of 16 and map to 0, making them transparent just as they were for 2 BPP mode. The other 15 colors in each offset will be rendered as opaque, so you'll want to arrange your palette to take advantage of this. The default X16 palette isn't great for this, but the first offset you see here has a standard diversity of colors and is good enough for a lot of applications. The second offset is also good, as that provides a linear grayscale, making monochrome tiles have excellent image fidelity at 4 BPP. The rest of the palette isn't much good for using as more offsets, so you want to define your own offsets that will work for you. As each pixel is represented by a nibble, you get 2 pixels for each byte, or a full 8x8 tile across 32 bytes, with each row represented by 4 bytes. This actually makes it easier to visualize what tiles are going to look like from the raw hex data, with 0 nibbles always being transparent and the rest always representing the same color index. As you can see in this rainbow example, it translates nicely to a hex dump. This is usually the sweet spot for most graphical applications on the X16, and makes its graphical capabilities most reminiscent of IBM PCs with EGA graphics, or Super Nintendo games that use the many 4 BPP modes. Finally, 8 BPP is the Cadillac of tile modes, and has similar space requirements for your VRAM garage. Even a little 8x8 tile is going to require 64 bytes, as each pixel is represented by a whole byte. You have access to the entire 256 color palette, but again, the 0 index will be transparent, so pixels specified by 0 bytes will not display the background color unless nothing is rendered underneath them. This is the only mode that will actually make use of the color indexes that are non-zero multiples of 16, which you can see by the default palette is what the intended use was. If you don't need a very diverse set of tiles, this mode can work and get you graphics reminiscent of original VGA graphics and the 8 BPP modes of the Super Nintendo. Like text maps, graphical tile maps use 2 bytes for each map entry, but the format is very different. Instead of only 8 bits for a screen code, you can use 10-bit tile indexes, with the upper 2 bits in the second byte of the entry. This is what lets you define up to 1,024 different tiles for each layer. The address of the tile in VRAM is calculated by starting with the tile base address and multiplying the tile index by the tile size in bytes. This means that tile 0 will be right at tile base, and tile 1 will follow it immediately, and so on through the rest of the tile set. You don't have to define the size of the tile set anywhere. The VERA will just try to get the data for whatever you specify. It may be garbage, but it's on you to set up your map correctly. The upper nibble of the second byte is the palette offset, expressed as the multiplier of 16 of the starting index. So 0 will get you the first 16 colors of the palette, 1 the next starting with index 16, all the way down to 15, which will get the last 16 colors starting with index 240. The remaining bits are used to define the flipping of the tile, horizontally and/or vertically. If both flip bits are clear, you get the tile as natively defined. As you can see here, setting one or both of the bits will flip it across both axes, but there is no option for rotation. So the X16 can't quite do mode 7 like a Super Nintendo, as only the whole display can be scaled, and nothing can be rotated at 90-degree intervals, much less arbitrary angles. We've talked quite a bit already about palette offsets, as they are quite integral to 2 BPP and 4 BPP graphics, but it's important to see this illustrated, specifically with the default palette. As we saw, color index 0 is always transparent, and each tile can have its own offset in its map entry. This means that even though we are limiting the number of colors in an individual tile to 4 or 16 colors, minus the color for transparency, we can have an effective 48 or 240 colors with transparency across the whole map. On this palette chart, we can see each palette offset visualized as a row of colors, with the first 4 available to 2 BPP tiles, and all 16 colors in the row available to 4 BPP, with the caveat of the first column always being transparent. We can see how changing the palette offset for a 4 BPP rainbow tile can change the colors. We see the original for offset 0, then grayscale for offset 1. You'll see that it's not based on brightness values of the first offset 0 colors, but on a linear scale based on the index, with 15 getting you pure white all the way down to transparent and black at 0. If you reorder the other offsets by brightness, you could actually switch to a representative monochrome tile just by changing the offset to 1. Then we look at the same tile at offset 15, or hex F. There we can see we still visualize the 0 pixels as black, as that is the background color, and the pink color actually at the beginning of offset 15 is ignored and just made completely transparent. The rest are different shades of magenta. For most applications, you'd want to change this palette to have more diverse colors at each offset that are going to work for different purposes, rather than these runs of 7 shades of the same color that just straddle randomly over multiple offsets. Transparency is also integral for graphics, as we talked a lot about that already too. What you need to visualize to understand layers is not just the 2 graphics layers that you define, but also a background layer that only has a single color, black by default. You can change that color at the very beginning of the palette by writing a new value to VRAM at hex 1FA00. This background color will show through if color index 0 is used for all layers at any given pixel. This is also true for bitmap layers and all sprites, as we'll see in future episodes. Here's an example of changing the background color from black to cyan by writing hex 0FF to color index 0. Then we assume layer 0 has 8x8 4BPP tiles, so we can place the rainbow tile there. Layer 1 will have 8x8 8BPP tiles, and our little Pikachu can live there. With no sprites, layer 0 will be directly on top of the background, and layer 1 will be directly on top of layer 0, and that's it. So with the rainbow and Pikachu tiles at the same position, we get the virtual tile on the right on our display. There we can see the background peeking through the pixels that are transparent for both layers, marked with a B for clarity. We can see all the opaque pixels of Pikachu marked with 1, and then the rainbow peeking through some of the pixels that are transparent around Pikachu marked with 0. This creates a nice little extremely low-res scene of Pikachu standing on the ground in front of a rainbow with a bright cyan sky behind them. Of course, this can be scaled up to much more detailed scenes, and then the tile layers can be controlled independently, including scrolling in different directions. We can control that with the VERA scroll registers. There are 2 pairs of scroll registers for each layer, letting you set 12-bit scroll values for both horizontal and vertical directions. Scrolling only works for text and tile layers, which is why the tile maps can be much bigger than the display. By default, both layers have scroll positions of 0 and 0, meaning the display will show the upper left corner of both maps. These scroll values are pixel-based, so you can scroll tile rows and columns partially off-screen. As they are 12-bit values, the maximum scroll value is 4095. The maximum dimensions of a tile map are 4096 by 4096 pixels, so we can completely scroll to the very lower right pixel and then roll over to the default position. 4096 is a nice big magic number that is an even multiple of any possible map dimension, so you can make any tile map scroll infinitely just by continually incrementing or decrementing the scroll values. As the upper nibbles of the high byte registers are unused, you don't even have to worry about masking those out, and just do regular 16-bit math to calculate scroll positions. We're going to see how this works with our example program. To keep it small and simple, we'll zoom in 4 times to make the display 160 by 120, so that a 32 by 32 map of 8 by 8 pixel tiles will fill the screen, with only a 20 by 15 tile grid visible at any time. We'll define both layers to use 4 BPP tiles, and use the same tile set, as we don't need that many different tiles. Layer 0 will be a sky with clouds that scrolls to the left at 30 pixels per second. Layer 1 will be a grassy field with trees at the horizon that scrolls to the left at 60 pixels a second, which will provide a parallax effect where the camera sees trees going past faster than the clouds. Since we're not doing any vertical scrolling, we only need to define tiles for the rows that will be visible for each layer. For layer 0, that means the top 8 rows only, as the rest will be hidden fully behind layer 1. For layer 1, we need to have the upper rows be transparent, so we can start that tile map right after the populated part of the layer 0 map, and then have the tree and ground tiles along the bottom down through the 15th row. After that, we don't need to populate the maps at all, as they will always be off-screen. If we disabled layer 1, we should see this boxed-in area of the display, including the transparent rows and the tops of the trees at the bottom of layer 0 that are normally hidden by layer 1. With only layer 1 visible, we would see this boxed-in area, with just the black background visible where the sky should be. And below that is just garbage. We won't bother writing to any part of the map that won't be seen. Since the minimum height of tile maps is 32 tiles, we have no choice but to have even the layer 0 map extend into the garbage. But it doesn't even matter. We can just put the tiles in VRAM right after the used parts of the maps as long as the alignments work. Normally at this point in an episode, we'd be going right to the code, but we need to show how we can plan all these graphics out, and a text editor is not the best place to do that. It takes a specialized tool called a spreadsheet. Yes, there are specialized tools for creating pixel art, but chances are that you already have this perfectly good tool for getting started at defining both tiles and maps. Here I have set up the first 8 columns to be the same width, which is the same value as the row height for the whole sheet. This gives us nice 8x8 tiles with perfectly square pixels. Then in columns J and K, I put in a visualization of palette offset 0. The colors are created by changing the cell fill colors, based on the actual colors in the default X16 palette. We can do the same thing when creating the tiles by selecting rectangles of cells and setting their background color. Chances are, your spreadsheet program will let you easily copy colors from one cell to another, letting you build a palette within your sheet. For tile 0, we will make it all transparent, which is a good general practice. This way, you can simply zero out the entries in the map that need to be transparent, which makes sense. Then we define tiles that we'll need for the sky. Most of the sky will just be empty, so we define a layer with all cyan, which is color index 3. Then we need some cloud layers. We can define a range of tiles by making a larger grid to the side. Here we have a 24 pixel wide grid that can represent a portion of the map that is 3 tiles wide. We define a big cloud as a 3x2 tile patch, which we can then break down into individual 8x8 tiles to the left. We take the upper left corner of the cloud to make tile 2, then the upper center for tile 3. Then for tile 4, we take the upper right corner as it's generic enough tile that we can flip it to make the other 3 corners of the big cloud. For the smaller cloud, we can just use tile 4 flipped each way, and that's it. But for the big cloud, we need one more to fill out the bottom center. So we make that tile 5, but flip it vertically. This way we could use it to make other shapes of clouds if we want, using flip pairs to elongate a cloud, for instance. We can plan out our map using the grid to the far right, indicating where we are going to put these big cloud patches and filling in a single small cloud to help bridge the initial gap. This grid gives us a representation of the full 32 tile wide map, and the first visible 8 rows. Then under that we can plan out the map entries for each cloud. You can see for the bottom row of the big cloud that we will have flipping bits set, indicated by the second byte of each entry. These indexes can all fit in the first byte of each entry, and we are only using palette offset 0, so these entries are fairly easy to read. Then we can plan out the ground layer. We have another copy of the palette copied down here for reference, and use the wider grid to plan out a patch that will contain a tree, bare horizon, and grass. We use a single tile to make a repeating pattern for the grass, which we place at tile 6. Tile 7 will be used for the bare horizon, and tiles 8 and 9 can be used for the trees. By making the trees perfectly symmetrical, we can save some tiles and just flip 8 and 9 horizontally to make the right half of the tree. We plan out the layer 1 map in a similar way to layer 0, selecting where we are going to place trees between bare horizon tiles. The first 6 rows are completely transparent, and the next 2 rows will be at least partially transparent so that we can see the sky between the trees and even the blades of grass sticking up over the horizon. We define the tree patches below, complete with flipping for the right half, and how those patches can be replaced with bare horizon by having another row of transparent tiles and just tile 7 side by side by side. So with all the tile assets designed, we're ready to implement them in our text editor. But first we need the standard stuff at the top, then some constants. We start with a 0 page pointer, then the IRQ vector that we're going to inject our own interrupt handling into. Then we define all the VERA registers we need, including the new ones we learned about earlier in this lesson. Mixed in with the register addresses, we have some values that we are going to use, like the vsync bit in the interrupt registers, and the display scale we are going to use. A value of 32 written to both scale registers will get us the 4x zoom we are looking for. Then we need to set up our VRAM layout, starting with our tile maps. As we saw earlier, we can have them overlap quite a bit, with layer 1 starting just 512 bytes after the start of layer 0. Luckily, this matches right up with the required alignment for tile maps. If we were to make the horizon just one row lower, we wouldn't be able to start layer 1 until hex 00400, wasting precious VRAM. But we aren't getting away with zero waste. We can start the tile set right after the last row we're defining for layer 1, which would put us at hex 003C0. The tile-based register requires a 2K alignment, so we have to start it down at hex 00800, which is 2K from the beginning. We could always try to reclaim that space in between with sprites, but for now it will just exist as uninitialized garbage, and that's fine as it will never be seen. We start our global RAM data with a staging of the sky map for layer 0. For each row, we define 32 pairs of bytes to represent all of its 32 tiles. Tile 1 is just plain cyan, and that's why we see most of these pairs are just 1 and 0, as there's no need to flip these tiles, and this empty sky takes up most of the space. You'll see patches in there like we defined in the spreadsheet for the clouds, and you could go ahead and add more clouds to this map if you want. Maybe even make some intersect with trees just above the horizon. Then we have the ground map, which starts with 6 rows of all transparent tiles, like we planned on the spreadsheet. Then we have trees and bare horizon, then a big field of grass through 15 rows. After the maps are defined, we define a label called nmaps to help define what the size of the map data is. We subtract the address from the beginning of the sky map from nmaps, and assign that to a constant. We can use this later when we copy this data to VRAM so that we know when to stop. Then we have the tile set, just as we defined in the spreadsheet, starting with tile 0, which you can see is all zeros for every nibble, meaning it will be entirely transparent. Then we see tile 1, which is all 3s, meaning flat cyan. And the tiles continue until we get through all the tiles we defined in the spreadsheet, and then we have another label and constant to define the size of the tile set that will need to be copied from VRAM separate from the map data. Then we have a macro called RAM to VRAM, which we will use to copy this data. For arguments, we will pass in the CPU RAM address of the data we loaded in above, the VRAM address it's going to be copied to, then the number of bytes that will be copied, which we can use those calculated constants for. The macro starts with a new control command called .scope, which we can use to define a scope for labels that won't affect the code outside the scope. This way, within the scope, we can define labels that won't create conflicts when we instantiate the macro in multiple places. We are going to set up VERA port 0 to start writing at the specified VRAM address, spreading it across the 3 address registers. Then we initialize our 0 page pointer to the CPU RAM address that we can index from to load the data. Then we initialize both of our index registers to 0, as they will be used to count each byte and determine when we have finally copied all the data specified by the numbytes argument. In our copy loop, we load a byte from RAM using our 0 page pointer and indirectly indexing it with y. Then we store it to VRAM data port 0. Our stride was set to 1, so the data port will auto-increment its address, so we just need to increment our index. We check the X register to see if we are on the last page of data that we need to copy, and if it is, we branch ahead to check end to see if we are done copying altogether. Otherwise, we check to see if y has rolled over to 0. If it hasn't yet, we are still in the middle of a page that isn't the last, so we branch back to the top of the loop. If y did roll over, then we need to increment x to start copying the next page of data. This means we also have to increment the high byte of the 0 page pointer so that we can keep indexing with y and get the next page of data. Then we branch unconditionally back to the top of the loop to keep going until we get to the last page. Once we are there, we branch to check end after each increment of y and check to see if it has reached the last byte. If it hasn't yet, we loop back to the top and keep copying the rest of the last page. Once it is done and x and y match numbytes, we fall out of the loop, as well as the scope and the macro. Then we continue defining some RAM variables, including a word to hold the default IRQ handler vector that we copy from its default RAM location, which we are going to overwrite. Then we define a counter to delay moving the sky layer and a constant for resetting it when it gets down to 0. Using a value of 2 means that every other frame will see the sky move, for an effective scroll rate of 30 pixels a second, while the ground moves by a pixel every frame for a rate of 60 pixels a second. At the start of our program, we disable the display while we configure and populate it. First, we set the display scale to 4x zoom, which gives us an effective resolution of 160 by 120 pixels. Then we configure layer 0, which will be the sky. We write 02 to the config register to specify a 32 by 32 map of 4 BPP tiles. Then we write the layer 0 map VRAM address to map base, shifting it to the right by 9 bits to get the upper 8 bits of the 17-bit address into the register. We do the same for the tile address and tile base, and we leave the lower bits clear to indicate 8 by 8 pixel tiles. This means that the display will show a 20 by 15 patch of the tile map at any given time while zoomed to 4x. Then we initialize the scroll registers to all 0, aligning the upper right corners of the display and the map. We do the same thing for layer 1, but this time using the layer 1 map for map base. Everything else is the same as layer 0. Then we instantiate our RAM to VRAM macro for each block of RAM we need to copy to VRAM. We do the maps first, followed by the tiles, using the labels and constants we defined earlier. Now both layers are fully configured and populated, so we can go ahead and re-enable the display, this time with both layers enabled. We also keep it in VGA mode, so the value we want is hex 31. Next, we initialize our parallax counter sky move with the delay value we defined earlier. This means that the sky won't move right away, instead waiting for the counter to go down to 0 after the ground has already moved a couple times. Before we specify a new IRQ vector, we need to save the current 1 to the RAM variable we created for that purpose, which will now hold the vector for the default IRQ handler, and we can call it indirectly from there. Then we go about overriding the IRQ vector by first disabling interrupts, then writing the address of our custom IRQ handler to the IRQ RAM vector. Then we make sure that only VSync IRQs are enabled for VERA by setting only the VSync bit. Then we re-enable IRQs, and the next VSync will trigger our new custom IRQ handler. Then we go right into our main loop, which only waits for interrupts in low power mode, then keeps looping forever. This means that the system will need to be reset to get out of the program, but that's okay. We could always check the keyboard buffer for a keystroke to break the loop, but we're just going to keep this simple. After the main loop, we define our custom IRQ handler that we used earlier for overriding the IRQ RAM vector. We start by checking to see if this was a VSync IRQ. If it wasn't, we branch ahead to @continue, where we'll just call the default IRQ handler. If VSync was indicated, we add 1 to the layer 1 scroll registers, doing a carry to the high byte register if necessary. Then we decrement the parallax delay counter in sky move, and if it's still non-zero, we branch ahead to @continue. If it has gone down to 0, we add 1 to the layer 0 scroll registers also, then reset the parallax counter to its initial value. Finally, we fall to @continue, where we call the default IRQ handler from the RAM vector, where we backed up its address. That's it for the code. We have a build script for this here in the Lesson 12 subdirectory that will build our program into tiles.prg. So let's go to the terminal and do it. Let's call build.sh, and then if we do a directory listing, we can see tiles.prg was built. So let's just start the emulator, and we'll maximize that to get a better look. Let's load tiles.prg and run it. And there you go. The ground is scrolling twice as fast as the sky, and it will keep going as long as we let it. So that's it for this episode. We have a lot more to cover when it comes to doing graphics on the X16, not to mention all the sound options and other built-in capability. We'll get to all that soon, but for now you can try playing with this program by making new tiles and filling out the map with more detail, just to see what it looks like. What you have here is the beginning of a game, and we'll see how to make graphical applications interactive as we learn more. If you don't want to miss any episodes in the future, make sure you subscribe to my channel and click the bell to get notified when they come out. If this episode taught you anything, please click the like button, and if you have any questions, please put them in the comments, and that can influence how future episodes are made. If you can't wait for the videos to go public, become a patron and get access to new videos as soon as possible. just like the folks you see here did on my Patreon page, which you will find linked in the description along with a GitHub repo containing all the materials for this tutorial series. Thanks for watching, and I hope to see you again soon. Bye-bye.